Hi everybody, today we are going to review exponential functions. So I'm not looking at this as the first time you've ever seen exponential functions, but more just of a refresher to get you ready for using this in calculus. So we'll go back and say, well, what was an exponential function? And basically an exponential function is anything we can write as f of x equals b to the x. But here, b is a number, so b is not a variable, it's going to be a number. We'll put in 2, 3, 4, whatever. It's important that that number b is greater than 0 and it is not equal to 1. As a quick reminder, because we will use this a lot, b to the 0 is 1, as long as b is not 0, which we wouldn't use anyway, and then b to the negative n will be 1 over b to the n. You could also write that as a fraction as 1 over b to the n. That might look a little better to you as well, to think that we're taking a fraction to an exponent, and I think you'll find these two little reminders super helpful as we go. So let's take our first example, keep it easy. We'll do f of x equals 2 to the x. So I picked these 5 numbers to look at to see what happens to f of x when I put in 0, 1, 2, negative 1, negative 2. So let's do 2 to the 0. We just said that will be 1. We can do 2 to the 1, that's 2. 2 squared we know is 4. And then let's look at the negative 1. Well, remember we said negatives become fractions, so 2 to the negative 1 is just a half, 2 to the negative 2 is a fourth. Let's take that then and graph it. So I have 0, 1. On the y-axis, I have 1, 2, and I have 2, 4. So you can see this graph is getting really big really quick. On the negative 1, negative 2, just do your best to kind of estimate where that goes. So between 0 and 1 is a half, kind of closer to the x-axis, I would have a fourth. And the idea is we're connecting the dots. Now when you connect these dots, this should form a curve. So this is going to kind of come up along the x-axis and pick up these lines. Now, I am not a super grapher, so let's look at that with a computer, right? Let's let it graph, and it looks more like this. That looks a lot better. And what we really just want to review again is what is going on here. So, important to say, first thing is the domain for any kind of b to the x. So here we're looking at b to the x, and specifically these b is greater than 1. Has a domain of negative infinity to infinity. So I could put in any number I want as the exponent. But what's really interesting is that the range is always going to be positive, because when I just take a number and raise it to a power, I'm not going to change its sign. So if I had a positive, it's going to stay positive. So we want to pay attention to that. And it's also important to see that this is 1 to 1. So every x I put in gives me a unique value for y. It's also important to see that this graph is always increasing, so it's going up, up, up as we go. If we turn that into a limit, because we've talked about limits a lot in calculus, so it's happening as I go to the right. So watch, as I'm going up, as x gets bigger, the function b to the x also gets bigger. So we interpret that as the limit as x goes to infinity of b of x is equal to infinity. As x gets bigger, b to the x gets bigger. Now on the other side, if we're looking towards going to negative infinity, right, so when x is getting smaller, what we can see is our function value is getting smaller. It's going down, 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 down. But as it's going smaller, it's not going down like negative values. It's getting closer and closer to 0. So the limit when x goes to negative infinity of b to the x is 0. Having this end behavior where we're going towards 0 tells me we do have an asymptote. And this asymptote would be a horizontal asymptote because we can see it is going horizontally, and it would be along y equals 0, which is just the x-axis. Example 2, very similar. This time I have 2 to the negative x. Now remember, we said negatives really flip into being fractions, and this time I'm going to write it as 1/2 to the x. Again, I'm going to put those same 5 numbers in. So 0, 1, 2, negative 1, negative 2. A half to the 0 will still be 1. A half to the 1 is just a half. A half squared is a fourth. When I put in negative 1, it's going to flip that fraction over. I get 2. And when I use negative 2, I get 4. So these numbers should look kind of familiar. Same numbers we had, just kind of rearranged. So again, we want to go back and we want to graph this. So again, I had 0, 1. At 1, it's small. It's only a half. At 2, it's even smaller at a fourth. Negative 1 gave me 2, and negative 2 gave me 4. So it really looks like our values have flipped around the y-axis, and this time our values are going down. And the big thing you should see that's different is the function is decreasing. I still have that same domain of negative infinity to infinity. I still have the same range of 0 to infinity. So I can put anything in, but I only get a positive number out. But the big difference I see is the difference between increase and decrease. That this was 2 to the negative x, which we wrote as 1/2 to the x, but this negative exponent, negative says decrease. So it really goes together, that negative exponent and our decreasing graph. So let me just write that for you so you can have that to write down. B to the x is increasing and b to the negative x is decreasing. If I'm looking at the limit as x goes to infinity of b to the negative x, so as I'm going to the right, it's getting smaller, 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 so this limit is 0. But then as I go to the left, so as x goes to negative infinity, my values are getting higher, 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 so that goes to infinity. Asymptote didn't change. We still have that asymptote running right along the x-axis. An important number to look at and revisit as we go to exponentials is the number e. E is about 2.71828. It goes on forever. It's kind of like pi in that it kind of hangs around and has this infinite number of decimal places. But what you need to know, it's between 2 and 3, but really closer to 3 than it is at 2. So we're going to use this value a lot, not only in this section, but in the whole class we'll use e and e to the x. So it's nice to look at the graph, and you really see the same kind of look. You can say it still goes through 0, 1. When I plug in 1, I get e, and here you can see this is 1, this is 2, this is 3, so right there, about 2.8, and then it grows from there. So it's getting bigger on the right, it's getting smaller on the left, but on the left it is going towards 0. If we look at the limit as x goes to infinity of e to the x, it is infinity because it's going up. If I just switch that around to make it e to the x, we said negative exponent, say we have a decreasing function, so here I have this decrease. If I put 1 over e into my calculator, I get 0.36787944412. Right, a smaller number. This number is between 0 and 1, but kind of on the smaller than a half size. And you can see it's decreasing, going down, 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 down. The two limits I'm asking you towards infinity are the ones you really need to hold on to because we're going to be able to use those in the class. And this one says the limit when x goes to infinity of e to the negative x. So as I'm going this way toward the right, I see it's getting smaller, smaller, smaller. Limit when x goes to infinity of e to the negative x is 0. What I'm wanting you to think about, e to the x is growing, it's not bounded. E to the negative x is shrinking, so it can only shrink to the point of 0. This is the difference between growth and decay. So grow, get bigger, decay, get smaller. It's the difference between appreciation, where things cost more, and depreciation, where things are worth less. So how quickly an exponential function turns is really determined by the base b. To show you that well, I'm going to go to Desmos and do a little interactive so you can see how it's growing. So what I have here is b to the x, and I put in this slider, and this slider lets me change the value. So I'm going to lay it down flat. There's b is equal to 1, and when I push play, you'll see the values grow, and it's showing you what it's becoming. So as that base got higher and higher, it got bigger and bigger, and then as it gets smaller, you can see it lay down flat again. So let's kind of step it through so you can see it. So here's 1, there's 2, 3, 4, right? And it's really getting bigger, so it's curving faster as I make the base bigger. And I only have this one set to go up to 10. So I want you to see that that curve happens a lot faster as the base becomes bigger. So let's use that idea that we can look at the base and see if we can figure out what's going on in this picture. So this picture has 3 curves. There's a blue one that's closest to the y-axis. There's a purple one that's a little farther out. And then there's a green one that's underneath the x-axis altogether. So let's start with the a and the b, 6 to the x and e to the x. Those are both positive, so that can be the blue and the purple. And what I see is 6 is bigger than e. So 6 being bigger than e says it's going to turn faster. So this blue curve would be 6 to the x. And then the purple curve, that will be e to the x. The negative 3 to the x then is the green one. And it's important to think about order of operations here. So we said b had to be positive, and it is. Our b here is 3. The negative is thought of as a transformation. So after we did 3 to the x, it flipped over the x-axis and it became negative. So let's try that again. I have 3 graphs. I have negative 2 to the x, 4 to the negative x and negative 5 to the negative x. So this is really us playing with the negatives and see if we know what that means. All right, what do we say? We said positive exponents increase, negative exponents decrease. Immediately I see b and c have negative exponents. I can see I have 4 to the negative x and negative 5 to the negative x. So when I'm looking at one that's decreasing, I'm really thinking that b, 4 to the negative x, should be this first purple one. Then I have negative 2 to the x and I have negative 5 to the negative x. So the negative outside of the 2 to the x said we started with a function that went up, and the negative flips it upside down. So we want to see which one of those look like that. So I have this green one and I have a blue one. So the green one looks like this flip upside down that we talked about. And process of elimination says, well, c must be negative 5 to the negative x. So let's see if we can do a few limits. We've been doing limits for a while. But here's what I want you to think about. We said when b is greater than 1 or has that positive exponent, it's going to grow. When it's a negative, it really means it's a fraction, so it's between 0 and 1, and it's going to get smaller. So I want you to think positive going towards infinity. I want you to think negative goes to 0. So the first one, I have the limit as x goes to infinity of 5e to the x plus 6. E to the x is going to infinity. So infinity times 5 plus 6 is still infinity. Then 2 says the limit when x goes to infinity of 10e to the negative x plus 50. Well, there's that negative. So negatives go to 0. 0 times 10 is still 0, but 0 plus 50 gives me 50. 3 says the limit when x goes to infinity of 3 times 10 minus 4e to the negative 9x. Once again, I have that negative. So e to the negative 9x is going to 0. 10 minus 0 is still 10, and then 3 times 10 is 30. That may sound like a lot. It might help out just to make it a little simpler to say this 4e to the negative x is going to 0. Then I can look at 3 times 10 is 30 and not have to think through all those other steps. So let's look at that as an application. Employees assigned to assemble electric bicycles for a company undergo on-the-job training. Data from the company shows the number of electric bicycles that can be assembled in a day can be modeled by the function n equals 36 times 1 minus e to the negative 0.15t, where t is the number of days of on-the-job training an employee receives. We're going to graph this function over the interval, starting at 0 and stopping at 30, and then we're going to find out the maximum number of electric bicycles an employee can assemble in a day. All right, so let's be smart. Let's go to Desmos to graph this. There's no reason to try to do this by hand. And so we can call it n of x. And what we said it was 36 times 1 minus e to the negative 0.15 x, because we called it x. So I know it was t originally, but now it's x in Desmos. We had a restricted domain that was 0 to 30. So here I can put set brackets. I do 0 less than or equal to x less than or equal to 30. Close it. And now it's restricted the domain, so I don't see anything before the 0. I can move over and scroll in if you want to, just to kind of see what's going on there. And eventually you'll see that this curves, right? So I see this curve that's happening. And where is this curve happening? Let's kind of zoom in so we can see some numbers. Here's 30, here's 40. The best guess should be it's this 36, right? We said e to the negative goes to 0. 36 times 1 is 36. So let's try just plugging in y equals 36 so you can see that line. Over time, as employees receive training, the highest number of bikes we expect them to assemble in a day is 36. Other places where exponents come into business calculus is compound interest. So let's review the formula. If you invest P dollars in an account earning R% interest compounded n times a year for T years, the amount of money A you will have will be found using the formula A equals P times parentheses 1 plus R over N to the power NT. So compound interest is the idea that you have a set amount of money P, you put it in a bank, and you walk away and you don't touch it. So you're not adding more money to it, you're not taking money away from it, you're just leaving it alone and letting it accrue interest. Let's look at some common compounding times. So annually means once a year, semi-annually would mean twice, quarterly would be 4 times a year, monthly would be 12, weekly would be 52, and daily would be 365. It will say within the problems what you're supposed to do, and you don't have to guess which number to use. So let's take our first example. How much money will you have in 4 years if you invest $10,000 at 2.5% interest compounded monthly? So let's label everything. 4 is the time, 10,000 is the P, what we started with, 2.5% is the R, and compounded monthly, that's our N. So we need to calculate A is equal to 10,000 times 1 plus R needs to be expressed as 0.025. Monthly is 12 to the 12 times 4. When you put this in the calculator, it's important, number one, that you try this, that you don't just watch me do it, but that you try it yourself. And what you're really finding out is how your calculator works. Some calculators will not do this multiplication in the exponent. You would need to tell it parentheses. Let's do it in Desmos so you can see what I mean by how to enter these. So I'm going to start by putting in 10,000, parentheses 1 plus 0.025 divided by 12, and then to the, so when I hit the exponent, here's where you can see the 4 times 12, and let me actually hit on my keyboard times so you can see me do it. Okay, now watch what happened. It looks like the 12 kind of came down, so I'm going to go back up to this 4, and I'm going to put parentheses, and this time do 4 times 12, and now I can see that number is up. So that's what I meant by watching your exponent. There's a difference sometimes between what you'll see on a handheld like scientific calculator or a graphing calculator and what you can see here. Let me also show you that. So I'm going to enter the same thing again, 10,000, parentheses 1 plus 0.025 divided by 12. And here's the part I want you to see. When I hit the exponent and I put 12 times 4, it stays in the exponent until I tell it to come back down. So I didn't have to put parentheses in my graphing calculator, but I need to in Desmos. One's not better than the other. It's just knowing how your technology works. When I hit enter, I get the same answer. So this is $11,050.56. Okay, let's consider another one. How much money do you need to invest to have $80,000 in 6 years if you earn 5.25% interest compounded quarterly? This time, the $80,000 is the A. We know what we want to have in the future. We're giving ourselves 6 years to get that money, so that's our T. 5.25 is the R. Really important, you always write that as a decimal, so it'll be 0.0525, and then quarterly is 4. I'm solving 80,000 equals P that we don't know, times 1 plus 0.0525 over 4 to the 4 times 6. When I put this in the calculator, I'm going to do it all at once. It's important that you don't estimate at any time or round at any point, so you want to put everything in the calculator in one big try. So we're going to put in 80,000 divided by parentheses 1 plus 0.0525 over 4. 4 times 6 is 24, so I'm just going to go ahead and write 24, keep things easy for me. 80,000 divided by parentheses 1 plus 0.0525 divided by 4. And then I hit the exponent, and we've already simplified it and made it 24. And it says $58,502, and we're going to make that 88 cents. Of course, the number is smaller, so when we're looking for what do we need to invest now to have a bigger amount later, we want it smaller. If we start with an amount of money, like the last one at 10,000, we expect it to grow, and that's how it became 11,000. Things that grow every second of every minute of every day of every year are called continuous. Occasionally that can happen in finance. It happens at other places all the time. Population, bacteria, so things that are biologic have a lot of continuous compounding, but we'll take a slight look at it from the aspect of money. So same P, how much money we're going to put in, same R, the interest rate we have, but when it says continuous, there's no N. There's no 1 plus R over N to the NT. It just boils down to A equals P e to the RT. Sometimes people call that PERT. Let's calculate how much money you will have in 3 years if you invest $15,000 at 1.2% interest compounded continuously. 15,000, that's my P, 1.2, there's my R, and 3 is my T. We have A equals 15,000 E to the RT, so this is 0.012 times 3. And I'm sticking with the TI for a minute, so we have 15,000. Now E is on my calculator twice when I look at it, so there's one time over the divide sign, and there's also this point which is over ln, and I'm going to use that one that's over ln because when I look at it I can see it says e to the x, so I know ahead of time it's looking for an exponent. So now I'm going to hit second, the e to the x, so it brings in e, it goes to the exponent, I can put in 0.012, and I'm going to say times our years, which were 3. And it says in the future we'll have $15,549.84. We're going to keep A equals PE to the RT, and let's do continuous growth. That'll make more sense for this formula. So the population of the United States in 2020 was 331 million. It's growing at a rate of 0.5%. We're going to write a function for the population, x years after 2020, and then we'll estimate the population in 2025. So we'll do a little forecasting. All right. Number one, be careful with this 0.5%. 0.5% means 0.005. Those are numbers that I do think are confusing sometimes, and you have to slow yourself down. Remember, 5% would be 0.05, and this is even smaller. You may want to put it in the calculator as 0.5 and divide by 100 if this is something that you just sometimes mess up how many zeros. Let the technology be your friend. So don't do this. We want to keep this one. So we're going to write down A is equal to, P was 331, and we know that's in millions. E is the same all the time. R was 0.005. So X is the number of years. Right now, we really can't tell that this has anything to do with the year 2020, but it's in our wording, so that's how we know. And we will use it when we get to the next part where we're trying to estimate the population in 2025. Here, X is only going to be 5. It's how many years have passed between 2020 and 2025. We're going to put in our calculator, A equals 331 E to the 0.005 times 5, our number of years. All right. This time I used Desmos just because I've used TI so often. So we have 331. And then E. So I can just type E on my actual calculator, and then I hit the exponent. I'm going to put parentheses so that it'll stay as the exponent. I have 0.005 and then times 5. So our answer says, in the year 2025, we can project the population of the United States to be 339.38 million. In this problem, we want to try to estimate the number of subscribers for the next 2 quarters for Connected Fitness subscriptions. So I've given you 8 quarters and the number of subscribers they had over those 8 quarters. You can see that the number of subscribers is increasing. You can also see it in this graph. So these are the same things. So we want to say, what do we think is going to happen in the next 2 cycles? So what's going to happen in the next year, quarter 1, quarter 2. So this took us to the end of 2020. Let's see what happens the first 2 quarters of 2021. This is definitely a problem for Desmos. So what we're going to do is we're going to take all of these numbers, 1, 2, 3, 4, 5, 6, 7, 8, along with the subscribers, and we're going to put them into a table. So first thing I'm going to do is push this add item, and we're going to add a table. And I'm going to put in the X values because they're easy. So 1, 2, 3, 4, 5, 6, 7, 8. So our 8 quarters that we had. Then I'm going to go to the Y's and put the corresponding values. Quarter 1 was 277, followed by 362, 457, 511, 563, 712, 886, and then we stopped at 1091. We could look at that by hitting this little zoom fit, so it's a magnifying glass, and it will bring in the values so we can see them. So you can kind of see this little curve going on. We have this one little higher value. Now to have Desmos turn this into an exponential function and we want it to be of the form ab to the x, I'm going to type y1, so that tells it to use the column. And then you go to the ABC on the keyboard, and down at the bottom there's this kind of swiggle, so this is making it do approximately. It's going to do a regression fit. So we're going to tell it y1, we want it to model, so tilde, we put that in, and I want it to be ab to the x, but our x is x1, so when I hit the exponent, I hit x1, again that's referring back to the table. And see how it brought that curve in, and it says here's a curve. There's one little other trick you're going to have to do here. There's this thing that says log mode. You want to hit log mode. It's just a different way that it's figuring out how this forms, but if you want your answers to match the answers in the homework, this is the way they're doing it so that you get your answers correct. So it gives it a little bit different. You can see here the A is 242.182. If I take it away, it says 236. So you want the one that's in log mode. That's the format we want to use. So this allows us to do a projection. Now watch, any assignment you have, it should tell you how many decimal places to use that to, so that you know how to do your calculations to get the next two. Since we're already in the calculator, let's do that right here. So I'm going to say f of x is equal to, and I'm going to call it 242.182. So I'm using all of the values, times b, 1.20262. And then to the power of x. That way I can put in the next two. So the two that I want, we wanted f of 9 and f of 10. This would be the next two quarters. So we knew what happened at the 8th quarter. We had 1091. This says if things continue to grow following this pattern, the next quarter would be 1274, and then the quarter after that would be 1532. So we just kind of watch how this grows, but super important that you pay attention to the wording. So however you are asked the question with how many decimal places, that's what you want to enter. The last thing we want to do is review how to solve exponential equations, and these will be kind of simple. We're keeping it to a certain kind right now. We'll do some more after we've done logs. So we're basically going to stick to the one-to-one property. This says if the bases are equal, the exponents are equal. So something like 5 to the x equals 5 to the 7th, that just means x is equal to 7. The bases were both 5, so the exponents have to match. Let's follow that same thought of 3 to the 2x equals 3 to the x plus 6. Both of the bases are the same, they're 3, which means we can say 2x equals x plus 6. This is a real quick one. I move the x over, it tells me x is equal to 6. A little bit bigger, I have 7 to the 3x plus 4 is equal to 7 to the 8x minus 6. I can drop the bases. I have 3x plus 4 equals 8x minus 6. Bringing the x's together, 3x minus 8x is negative 5x. And then when I bring the 4 over, that becomes negative 6 minus 4, which is negative 10. Divide both sides by negative 5, you end up with x is equal to 2. Here I have 4 to the 2x minus x squared is equal to 4 to the negative 8. Drop the 4's, I have 2x minus x squared equals negative 8. Now that I made this bigger and it's become a quadratic, we want to make sure we set this equal to 0. I'm going to move everything to the right and I'll have a 0 on the left. The negative x squared becomes positive. The 2x is now negative. And I still have minus 8. So I want to factor. I'm looking for factors of negative 8 that give me negative 2. This will give us x minus 4 times x plus 2. Solving that gives me x equals negative 2 and x equals positive 4. Now let's try x e to the x plus 9 e to the x is 0. So this time I don't have just two things, and I can't make them exactly equal because I have this coefficient of x and the coefficient of 9. So instead what I want to look at is, well, what do these two things have in common? And hopefully it just screams at you that it's e to the x. So let's take that e to the x out. When I take the e to the x out, I have left x plus 9. This is still equal to 0. So I have two factors. I have e to the x and I have x plus 9. Well, I have this little reminder for you that e to the x will never be 0. Anything b to the x will never be 0. It's always going to be positive. Remember, our range was 0 to infinity. So I don't have to worry about the e to the x. All I have to do is x plus 9 equals 0, which says x is negative 9. Here's our last one. I have 6x times e to the negative 2x plus 3x squared e to the negative 2x is 0. This is a lot like the last one. I have two things going on that are both e to the negative 2x, but they also are complicated by coefficients. So let's take step by step. I see the 6 and the 3. Well, I can take a 3 out. I see x and x squared. I can take an x out. And then the e to the negative 2x is the same in both, so let's take that out. So then what's left? Well, 6 divided by 3 is 2. The x has already come out. The e to the negative 2x is already out. Then I have 3 divided by 3 is 1. X squared divided by x is x. And then e to the negative 2x is out as well. You could choose not to put the 1 in front of the x. I did it just to kind of emphasize what we're doing. This is the first time we're really factoring a lot. With the 3x e to the negative 2x, the only thing I'm concerned about is this x. The only time 3x e to the negative 2x is 0 is if x is 0. Then the 2 plus x being 0 says x would have to be negative 2. So that's the end of our review of exponentials. Next time we'll look at logs and kind of put it all together before we go back and do some derivatives.